welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. And as you already know, sometimes not in Luxembourg, and sometimes we have international episodes. And today is actually the case of an international episode because we have Journées Arithmétiques happening in Luxembourg and we have some important guests coming here. But before I introduce them, I also wanted to say that we are proudly powered by Research Luxembourg and recording at the Media Center of the University of Luxembourg. And now on to the guests, because I guess you are more interested in that than who supports us, because you know that by now. We have the first guest, which is Professor Jennifer Balakrishnan, who is Professor of Mathematics at Boston University, and she got her bachelor's degree at Harvard University and PhD in mathematics from MIT. And on the other side, you can't see one, on the left side from where I'm sitting, we have Tim Seuré, who is a doctoral researcher at the Department of Mathematics, FSTM of the University of Luxembourg. Jennifer and Tim, thank you very much for coming today.
Thank you for having us.
Hello, thanks for having us.
What are Journées Arithmétiques, Jennifer?
It's a conference in number theory that's really international in scope, and it happens every 2 years, and it brings together hundreds of mathematicians from across the world to celebrate number theory, to hear lots of really exciting lectures, and a lot of young people too who are very enthusiastic about the subject.
So you said number theory, so let's discuss that. What is number theory?
There's several different things. So one is questions that are very fundamental in nature about numbers, such as the prime numbers. So these are the numbers that have just one in itself as the factors. So 2, 3, 5, 7, and so on. And in some way, these are the building blocks, really, of the rest of the numbers. There are many fundamental questions you could ask that involve prime numbers. And another thing that number theorists like to do is to study various equations and their solutions over whole numbers or other related number systems.
Okay, but there is also the application of number theory. Then cryptography, is that application or is it theoretical? I always struggle with that.
Yes, so I do my PhD in cryptography, and I would say cryptography is really more application, right? Even though you do study it also from a theoretical point of view. A lot of cryptography also uses prime numbers extensively because they make things much easier to study, and they do satisfy a lot of properties that non-prime numbers do not. And in cryptography, we make use of these properties.
When I read about you, Jennifer, there was number theory, okay, and then there was arithmetic geometry. And for me, it's arithmetics and geometry. I did not mix them together. So what is that?
Arithmetic geometry, one way to think about it is number theory meets algebraic geometry. And in school, I think, you see a little bit of this as well. Maybe you don't quite call it that. But when you think about equations, like x plus y equals 2, you think of that maybe through algebra, but you can also plot, the line that describes. And that's a little bit of geometry. And algebraic geometry is, maybe upgrading that to polynomial equations and maybe more complicated geometric objects that arise. But it's using that tool to study number theory as well.
But then again, from school, I have a feeling that it's all clear. There's not much to study anymore. You take the equations, they work. There are some, geometry, you understand it. Where are you going deep?
Right. Okay. So, yeah, I think that's interesting, right? In school, you see equations and then you learn different ways to solve those equations. But actually, I think the story kind of stops in a way that is perhaps unsatisfying because you quickly learn their equations just beyond what you learn in school, where we, like humanity, does not know how to solve them. So I think a very simple statement of this is, you often learn how to solve quadratic equations in school. But if you were to change the degree, and if you think about an equation in 2 variables, which you also see in school, so like x squared plus y squared equals 1, that defines a circle, a unit circle. But if you were to change that equation by 1 degree in x, so if we were to look at an equation like y squared equals x cubed plus 1, that is what we call an elliptic curve. And elliptic curves are such a fundamental object of study in number theory. We don't yet have an algorithm to determine all rational solutions to that class of equations. We have one that would work if we knew that some object were finite. But that's a big open conjecture. So there are questions like that. And of course, if you change the degrees of the equations or you change the number of variables, different things change. And so there are a lot of exciting questions to be studied.
And this is what you like in cryptography as well, because it all bases on the fact that we can't solve certain things easily, right?
Yes, exactly. So for a cryptographic scheme, we are usually basing this on problems that we know are very hard to solve in practice. So maybe there exists an algorithm to solve it, but this algorithm might take a very, very long time. And this is what we base cryptography on. And these problems, they typically stem from number theory. For instance, it might be a problem which I think you might already have talked about in a previous podcast. It's about simply factoring a large integer into its prime factors, right? It's easy to do this with small integers, but once we have huge integers, like let's say of 500 digits, it becomes basically impossible to do this in a reasonable time with a computer. And problems like these, which are very hard, they are then used to build secure crypto schemes on.
But we have a problem with that, because that all bases itself on the fact that there are no quantum computers, right?
Yes, exactly. So some problems which are hard to solve with classical computers, they might become easy to solve with quantum computers. And the problem that I just mentioned of factoring a large integer into primes will become somewhat easy in the future. Once we have quantum computers which can apply certain algorithms without many errors.
But I jumped to quantum computers, and listeners, remember that if you want to go really deep in quantum computers, there was an interview with Professor Ignacio Cirac where we talked about one of the ways that most probably quantum computers will work in the future, because as Tim said, might. This is also, there's a lot of hype about it. We still don't really have a quantum computer, at least in my definition of this word. But he also said primes. So going back to the primes, actually, I know, Jennifer, you prepared a pub quiz question for us about primes, but special kind of primes. So let's tell the listeners what the primes are and then what the question is, of course.
A Mersenne prime is a prime of the form 2 to the p minus 1, where p is a prime number. And the question is, how many Mersenne primes are known?
And listeners, remember, answer only at the end of the podcast. But when I was preparing for this interview today, I noticed I always like to see what the guests also teach. And I was very surprised, because I think you are the first person that is also doing a little bit of science communication during your courses, in the sense that you give your students an article, right? A mathematical article, and they have to take roles. Can you tell us a little bit about that? What happens in those classes?
That's right. All right. I love this class. So it is modeled after a class former colleague of mine, Nick Trefethen, taught at Cornell. And so the idea is that you cover some of the classic papers in your field. So I call it greatest hits in number theory. This semester, I think greatest hits in arithmetic geometry. But what we do is we pick some selection of papers, and the class as a whole, we all nominate papers, and then we spend the first 2 days of the class very quickly reading through the papers, just kind of at a very high level to understand which ones do we think we can do this semester. And then we vote. And each paper we cover in 3 different ways. So we have a mathematician, and I take on the role of mathematician the first day, kind of giving a very broad overview, setting the landscape, the context, what things came after this, why is this a greatest hit? And the students also take some of the mathematician roles, so in the subsequent days, depending on how many days we devote to the paper. But then we also have an experimentalist who prepares some computations or some, computer-guided work on the paper. And so part of the work of the course is to try to figure out some natural experiments or computations to do. And then the final role is that of a science journalist, someone who will kind of digest everything that's happened, also take into account the article itself, and then to write something. Could be aspirationally, say, quanta level article. But for other articles, we've had, kind of an expository piece that's written maybe targeted at PhD students, early PhD students, or PhD students who are farther along. And it's been very interesting to see how the students take this on. And then we read through the draft in the class and then discuss and, present some constructive critiques on the work. And I think it's been really wonderful to see how the students take this on.
Of course, because there is this theory that if you actually have to explain it to maybe not a 5-year-old, Quantum magazine is not for 5-year-olds, but still to someone else that doesn't have the knowledge, then you actually really understand it, right?
That's right. I think it takes quite a lot of work to communicate mathematics or science, as I'm sure you know. And for a lot of students, it's maybe the first time that they're actively asked to try to communicate this to an audience maybe different from their peers, right? To say, explain this to a general audience and to kind of go outside that comfort zone of just kind of communicating that technical way that you're used to.
So let's wear two hats today. So first of all, the hat of a mathematician, because I have to say that I was trying to read some of the mathematics articles. And there are certain scientific articles where I can read them, more or less. And there are certain ones that I don't even know where to start. I mean, it's just too complicated. So actually, students, when they start studying mathematics, are they really able to understand what is inside a scientific article or not?
I think a lot of the articles, maybe they already have a reputation. And so students have heard of these articles as being some of the most famous advances in our field. So one I think is particularly striking is this work of Gros and Zagier that really is just kind of known as Gros-Zagier. So it's their work that describes the height of a Hegner point and relates it to the derivative of an object known as the L function. And this article is so famous, and of course Gros and Zagier wrote other articles together, but this one really, if you're talking about Gros-Zagier, people will think about this article. So I think many of these students have seen in some form either, they've already heard a seminar where, the speaker will casually refer to that argument or that result, but they haven't had maybe the time to read that article in full. So we'll have articles like that are suggested. Other students will bring articles that maybe they've wanted to read for some time, maybe for their own research. But we get so many different things. It's really maybe the toughest job is at the beginning to narrow it down to just, the set that we'll cover that semester.
But I assume that probably you don't discuss your own publications, right?
Never. I've never tried to do one that, and I mostly, co-author with a number of collaborators, but no, for the greatest hits, we're kind of looking at things that have really kind of become famous for a number of decades.
Well, you know where I'm leading, I guess, because of course I wanted to talk about the cursed curve. When I was preparing, there was a Quantum magazine article as well about what you found. Let's say you are writing a Quantum magazine article about that problem. How would you explain it to our listeners? What did you solve? Because honestly, I was trying and I read a lot. And then I went into the rabbit hole of rational points and then rational points on a curve. And I still can't explain it probably as well as you can.
All right. Well, let me try. So I think one of the fundamental questions that we like to understand in arithmetic geometry is determining the rational solutions to particular types of equations. So there's a very famous theorem of faultings from the 1980s that says that a curve of genus 2 or more over the rationals has finitely many rational points. And so let me try to unpack that. Okay, so first this was conjectured by Mordell over 100 years ago in 1922. There are various equations that you could write down, and if the equation is written in two variables, x and y, that defines a curve. Let me give you an example of a curve of genus 2. So the equation that's y squared equals x to the 5th plus 1, that describes a curve of genus 2. And there are classes of curves that are quite interesting, known as hyperelliptic curves, and you can read off the genus really from the degree of the equation. So that's quite nice. And in general, there's kind of a classification of the rational points on curves. In genus 0, this is well understood. So genus 0, this is like conics, like that circle that we were mentioning earlier. And something called the Hasse principle describes exactly the rational solutions. In genus 1, genus 1 curves include the class of elliptic curves, which we talked about earlier, that play a role in cryptography. And in genus 1, if it's an elliptic curve, well, then turns out that the rational solutions, they have a lot of structure. They form an algebraic object known as a group, and this is very important for various reasons. And then in genus 2 or more, by this work of faultings, there are only ever finitely many solutions. So now that we know that there are finitely many solutions, we would like to find those finitely many solutions. And the cursed curve that you're describing, it's a curve of genus 3 defined over the rationals, and you can write down an equation in terms of x and y. And it's known, of course, that there are only finitely many solutions. But what wasn't known was, had the people who studied this before, did they find exactly all of the solutions, or could there be more that hadn't yet been found? And one technical reason that this was challenging was that in kind of the ambient geometry that you kind of position these curves in, you take the curve and you put it inside this object known as this Jacobian. And the Jacobian of this curve is rather complicated, relatively speaking. It has an invariant known as the rank that's larger than kind of what you generically expect. It turns out that the rank is 3. And so if the rank is less than the genus, there is a method that was originally due to Chaboty and then later enhanced by another mathematician, Coleman, that really does a lot of work. And so, essentially, if the rank is less than the genus, that plus possibly some other methods will do the job for you, and you'll be able to determine rational points. But when the rank is equal to the genus, you're kind of in this new territory. And so that was some of the work that my collaborators, Nathan Dugra, Stefan Müller, Jan Tautman, and Jan Vonk, that we worked on a particular case of this idea of Mignon Kim to extend Chaboty to this particular case.
I'm very happy you mentioned Chaboty because I was actually looking into podcasts, whether there's any podcast where they're discussing it. There's none. So now we can tag it. There'll be a podcast where we're talking about that as well.
Oh, that's great.
By the way, why is it cursed curve?
Oh, okay. That's an interesting question. So why is it the cursed curve? There is a conjecture due to Seuré about images of these so-called residual Galois representations attached to elliptic curves. And essentially, as the story goes, we kind of understand that to solve this problem, there are kind of 4 categories, 4 different types of these Galois images that you need to study. And the case of the split carton, this was done by Bilou and Parent, so we understand Seuré uniformity in this way. But the further work of classifying all rational points or all points with rational coordinates, these rational solutions to so-called split carton modular curves, this was taken on in further work by Bilou, Parent, and Rebolledo. And in this article, they essentially classified all of the rational points on the split carton modular curves except for level 13. And they refer to it as the cursed level for a few reasons. And I think they're somewhat technical in nature, but one of the surprises was that this level 13 split carton modular curve turned out to be isomorphic to the non-split carton curve of level 13, by which we mean that really the equation that you could write down for the split carton level 13 curve is exactly the same as the non-split carton curve of level 13. And this was a huge surprise. And the non-split carton curves are essentially the most difficult in this classification that I was describing earlier.
Okay, and that's why cursed from the beginning, but also level 13, maybe it's also the 13 number. I don't know, in some cultures it's unlucky, no?
Exactly. And I think the numerology of that, together with some of, I think there were a few other kind of distressing things that happened, some coincidences that seemed to just happen at this particular level. And so it was the cursed level 13.
I love the fact that you're talking about emotions, about distress, cursing and whatever, right? It's a lot of that, which is great, right?
I think it did cause a lot of distress. That, somehow there are these very robust methods, and yet somehow at 13, none of them seem to work.
It's really impressive, right, Tim? So now it's, the ball is in your court in the sense that we said cryptography, okay, fair enough, we understand, but you're actually studying a very special type of cryptography. So I'm counting on you that you will explain it as clearly as Jennifer did. What on earth is it? What's the name? I have to actually read it because, again, I don't remember. It is fully homomorphic encryption. What is that?
First, cryptography, right? It deals with, let's say, securely transmitting messages, for instance, on the internet. And what you do is you start with a message. Usually you translate your message first into a mathematical object, which can be just a number or a polynomial or anything, and then you encrypt it, right? So which means that you perform some computations with your original messages or your message, and then you end up with a new mathematical object, which for a third person is somewhat, they cannot really interpret it. They do not know what message really lies behind this new object. And then you send this via the internet to the person you want to send it to, and then they can undo the computations that you have done with it originally to get back the message that you have started with. Okay, so this is the typical way you encrypt messages, and fully homomorphic encryption adds another layer on top of this. So maybe I can start with an example which I personally find a little bit fascinating or surprising maybe. It's the following. So you start, let's say, with a picture of a person. Okay, let's say, just to make it a bit more concrete, let's say of your grandmother. Okay, and you want to print out this picture for your grandmother's birthday, but you want to make it a bit funny, so you want to put on a hat on her head. Okay, you could do it maybe yourself, but you know there exist some very good algorithms out there which can do this way better than you could do with any Photoshop skills that you have. Okay, so you decide to use an online tool for that, which does this in a second, and it does it very good. But okay, maybe you don't necessarily want to upload a picture of your grandmother to the internet, even though it shouldn't be shared, but you never know, right? And you don't want a picture of your grandma to end up in unsafe places, right? So the idea of fully homomorphic encryption is that you go ahead and take your picture, you first encrypt it locally on your computer, and then instead of uploading your picture in plain text, you upload it in ciphertext. So the tool that you want to use, they cannot really see the picture. They only see the ciphertext that you have uploaded. And still, the tool is able to apply their algorithm on this ciphertext. So they are able to put on a hat on your grandmother's head without even seeing the picture. They produce a new ciphertext encrypting your grandmother with a hat on, and they then provide you with this new ciphertext, and you can download it and decrypt it locally again, and there you go, you have a picture of your grandma with a hat, and nobody ever saw this picture except for you, once you have decrypted it. Okay, and this is made possible by fully homomorphic encryption. This was just a very nonsensical example, but you can also imagine that this also works with all kinds of other algorithms. In fact, it works for any algorithm that you can think of. And that's the beauty of fully homomorphic encryption. No matter what circuit or algorithm you want to apply onto your data, you can do it with fully homomorphic encryption.
So why isn't it done yet everywhere on the internet?
Yes, so the problem
there has to be a problem, right?
Yes, so okay, this specific example of putting a hat on, this already exists, but maybe there's not so many people who really want to put a hat on their grandma's head. But the problem is that it's somewhat inefficient these days. So if you want to have numbers, basically if you want to apply an algorithm homomorphically, so on the ciphertext, it is as good as applying the algorithm in plain text, but on a computer from the early 2000s. So, back then the computers were not so fast if we compare them to these days. So we cannot really do very exciting things these days. So the challenge really lies in finding new schemes, maybe, which allow us to do this, but in a somewhat efficient way. We know it's never going to be as efficient as doing it in plain text, right? I mean, that's the nature of cryptography, but still we would like to be able to do it somewhat more efficiently.
So there is a lot of mathematics behind it that you need to figure out right now.
I mean, I don't know how much mathematics there is going to be behind new schemes, but already the ones we have, the not so efficient ones, they're based on mathematics, indeed. I mean, I don't want to say it's hardcore mathematics, because I think whatever Jennifer is doing is going to be 10 times harder than what I am doing. But still, I think it's already sufficiently advanced, because otherwise we would have found a very easy algorithm already for it.
Yeah, I guess so. Yes. You put computers back in the picture, so we're going to move to computers in a second, because, of course, I think I'm trying to avoid an episode without discussing AI, but nowadays there's AI always at certain moment. But before we do that, actually, I did not start with it, but I still wanted to know your opinion, Jennifer. So what is actually the task of a mathematician? Is it just finding proofs? Am I right? You're all the time trying to prove new theorems, or is it something else nowadays?
I think a mathematician can have many jobs. There are many things a mathematician can do. I think some mathematicians, they are indeed, proving big, important results. They're building theories. They have a program that they're furthering. I think other mathematicians are maybe building tools. Others are doing computations that will further elucidate, general phenomena that maybe one day will be proved. Some mathematicians are more experimental, right, where they're, maybe behaving like a scientist, trying to understand what exactly is true. And I think it takes all types of mathematicians, right, to further mathematics and enterprise.
But the division is not so clear cut, like in case of physics, that you have the theorists and the experimentalists? Or is it already happening like that?
I think everyone probably perceives themselves, somewhere on this continuum. Tim, maybe, you probably see where you are. Personally, I think I do both. I compute and I also try to prove things. But yeah, certainly, I think some people will find themselves, at more one end than the other, and others, do all sorts.
I recently read an article about exactly LLMs, AI, generative AI, and whatever. And of course, we are nowadays treating it as a tool. And you could argue that it can speed up certain processes, maybe even proving a theorem. That's why I'm asking, how do you see the future of your work? Do you think mathematicians will be using these tools more often? Or do you think the divisions are already there? As you said, certain people are more into computational approach and certain are a little bit more outside of it.
Yeah, it's really interesting to think and to speculate where these tools will take us over the next few years. I think those who are involved in computational work are already seeing these tools have a tremendous impact. If you're programming, certainly these tools know a lot about writing code and they can help streamline tasks like those. There are those who are working formalization, and I think there are interfaces between proving that, you might do by hand and then proving that you might do with the tools of formalization. And so I'm thinking about languages like Lean that people use. But I think a lot of people are still kind of starting to work with these tools, and we haven't really seen the whole community embrace the use of these tools. So I think there's still a lot that we're not sure about yet. So one of the jobs during this Greatest Hits course is to come up with some experiments for the paper that we were discussing. And I remember being particularly stuck. We were going to do this brilliant article, actually, of Peter Schulte, who gave one of the morning plenaries today. And it was from one of his ICM lectures. And I couldn't come up with an associated computational experiment to do related to perfectoid spaces. And then one of the students in the course said, hey, this was recently formalized in Lean. We could talk about Lean and what it means to formalize mathematics. And so Kevin Buzzard had something called the natural numbers game at the time. And so we all played this natural numbers game and got through various, he kind of gamified this process of formalization. And it was pretty cool to explore and to see what this completely new direction to many of us was to proving things in mathematics. Then more recently, we, in this era of generative AI and large language models, we were discussing, what it means to write. And we kind of ran through this as an experiment, and we gave the same prompt to a number of these large language models. So Gemini, some version, ChatGPT, some version, Claude, Sonnet, and so on. And we gave them a prompt to write a Quanta-style article about this work of Grossage. And we compared all the different things that came out. And I think we also tried, write a version for PhD students, write a version aimed at experts, but short. And it was really interesting to compare the different things that it said. In one of the technical versions, it actually got the statement of the theorem completely wrong. And that was a huge surprise, because you thought of all the things it should quote from the paper, but it was a little creative in what it chose to do. In the Quanta-style articles, it was interesting that many of them we could kind of see that there were choices made, starting with a nature analogy, starting with a building bridges analogy, starting with a music analogy, and then, weaving in the analogy as it went through. So I think for a lot of students, it was interesting to see how these tools could be used to write. Certainly, I'm sure many of them have been tempted to use tools like this, but also to be wary of the pitfalls, right? That these things do make mistakes, and to know that you should read things that it produces with a critical eye.
How is it in cryptography? How much is it embraced right now, already applying, helping, using it as a crutch, let's say? I don't know how you want to call it, really. AI, generative AI, proving, I don't know, anything.
I don't think it's used much more than it is in mathematics, really.
I personally, from my podcasting side, have to ask a lot of questions about creativity, what it means, how do you differentiate yourself from others, right? And whether we'll be all producing the same type of content in the end because we'll be using these tools, or will there be certain kind of, application of critical thinking on top of it that will differentiate us? And also, in general, is it about knowing a huge collection of facts and then putting it in common ways or not? That's my question in general. It's a very high level going out of your expertise right now.
So you made the point of creativity, right? And then one can ask whether or not an AI is ever able to be creative itself. I think we should first ask the question, what is creativity to begin with, right? And personally, the way I see creativity is that really it's just recombining stuff you already know in perhaps surprising ways, right? That's how I see it. And if this is really what creativity is, then I think an AI is definitely able to do this, right? Maybe even someday better than human beings are, because AI is able to collect a lot of different ideas, maybe much more than a human being is ever able to collect. And it can then also recombine and see, okay, this doesn't work or this doesn't produce anything new or useful. But then it can reiterate until maybe it does find something which can be of use. Again, if this is what we think of creativity as creativity, then I guess one day AI might be able to help us mathematicians to make progress.
I'm asking also because, there are certain people who argue that, especially the ones that never liked mathematics at school, that creativity and mathematics, that they are two different things. And I just really believe that for me, from my personal perspective, it was one of the most creative subjects I could imagine. So that's why I think it also goes together with the discussion of creativity and AI. But then playing the ball back to you, Jennifer, for the greatest hits, when your students are voting, what do they actually look at when they choose? Do you know? What is the reason why they choose? And why would you choose certain hits over other ones?
Yeah, that's a great question. I wonder why they choose what they do. I think some of it is just kind of the aura, right? They've heard about some of these articles, but maybe they've never had the time to do it all on their own. Certainly, some of them will lead a reading group with their fellow graduate students where they'll maybe do one paper over the course of the semester. But here, the idea really is to try to do something fast, right? To take some things in so-called black boxes where you don't really understand all the ideas, but you kind of understand the main steps, and then to use that as kind of one thing then allows you to move to the next. And so to kind of make those leaps of thought that will let you navigate the whole article. I think some of them will just kind of pick articles that they've been wanting to learn more about, and others will pick things that just, came to them the day before that another student mentioned to them. So I think we really do all sorts of things.
It's also interesting why they've been wanting to do it, right? Where it started, where did they hear about it? Well, I know you can't answer for your students, right? But does it happen sometimes that you have one of the articles on the list and you really want to discuss it with students and they're absolutely not interested?
Oh, definitely. That certainly has happened. So one of the articles, and this is an article that I think transformed a lot, at least in the modern era of computation, was one of the articles of Birch and Swinnerton-Dyer, where they did these computations on a computer kind of as big as this room, and they found this wonderful, mysterious relationship between some collections of numbers that really, were surprising. And this led to a conjecture known as the Birch and Swinnerton-Dyer conjecture about the algebraic rank of an elliptic curve, one invariant, being related to an analytic object attached to the elliptic curve. So the algebraic rank being equal to the analytic rank. That's the statement. But it really came from looking at lots and lots of data that they produced. And for some reason, the students have not yet picked that article to do in the various iterations of this course.
So you're still waiting?
I'm still waiting, still hoping. Yes, I keep it on the list every time.
Because in case some of your students are listening, that's a hint. Next time,
Let's
please
do
choose
that one.
Let's do that one. Okay, but we're going back all the time to what you did in the past. And now, once you're back in Boston, what is waiting for you? I don't know, a blackboard full of stuff that you need to solve, or a computer with something you need to work on? What are you working on right now?
Oh, yeah, lots of different things. So one thing is to kind of, in the vein of what we did with the cursed curve. So we used this technique that we developed in the paper called quadratic Chaboty, which is a kind of generalization of those Chaboty-Coleman techniques I mentioned earlier, but we're trying to apply quadratic Chaboty to new classes of curves. So, there's the cursed curve and other modular curves. So curves that come to us from classification problem, because if we understand these rational solutions, they tell us about other objects. So for instance, elliptic curves with some extra structure. So there are a number of modular curves for which we'd like to understand their rational points. And we have a whole list. And so, non-split or split 13 was one. We recently did non-split 27 with a group of people. So Alex Betts, Daniel Hast, Ashraya Jha, and Stefan Mueller. And we're looking at other non-split Cartan modular curves and other classes of genus 3 curves where we hope to better understand rational points.
Okay, we're talking curves with Jennifer, and Jennifer kept saying that, there is a lot of application of number theory and other of the stuff of her expertise into cryptography. And to be honest, again, if I think of cryptography, I think about, passcodes, how do you call them, even like keys, if you want. I think of certain set of numbers. I don't think about dimensions, curves, and all that. But should I be thinking about it? I understand what is the result, but what kind of mathematics are we basing ourselves on? What is the nitty-gritty details behind it, and what are your small brick in it? Maybe
I can first talk about what the current fully homomorphic encryption schemes are based on. So they are based on the hardness, or actually the assumption of the hardness of a very special problem in number theory, which is called the learning with errors problem, or also other problems which are related to it, for instance, the ring learning with errors problem. And just to reiterate, it's an assumption. We assume it's hard. We haven't proven it yet, although we assume that it's both hard for a classical computer and for a quantum computer. So we assume that the schemes that are based on these assumptions, they are going to be quantum safe. So anyway, I will not explain this learning with errors in detail, but still I want to give you a glimpse into what this somewhat is. So assume that you just want to encrypt an integer. Okay, let's say 5. And for these schemes to really be secure, you cannot go ahead and take 5 and encrypt it. But what you go ahead and do is you add a little error to your integer. Okay, so instead of encrypting 5, you add an error, let's say 0.01. Okay, so you go ahead and encrypt not 5, but 5.01 instead. If you do this, where the error is, by the way, at random, okay, you do not always add 0.01, otherwise, okay, it would be very trivial, but you add a random error to it. And adding errors like this makes the schemes secure. Okay, and the assumption is that you cannot really learn anything, any secret knowledge, because of the errors. Okay, learning with errors, you're not able to do it. Okay, and now you should think about what we try to do in these fully homomorphic encryption schemes. We try to go ahead and compute with these encrypted integers. I'm saying integers just to simplify it, but sometimes we can also go ahead and encrypt polynomials to which we have added errors. But now if you take, for instance, an encrypted 5, so let's say it's 5.01, and you have another encrypted integer, so let's say 10.1, okay, with a bigger error this time. If you compute with them, let's say you multiply them, you actually make the error increase. Okay, so I don't know. I don't want to figure out what the error is in this case, but it's going to be bigger than the error that you have started with, right? And well, if the error is sufficiently small, like for instance with a 5.01, you can still get back your integer that you have started with, right? You just need to round to the nearest integer. But at some point your error is going to be pretty large, right? So if your error is 0.4, well, then you can still do the rounding, but you get close to the threshold, right? You can, at some point, the rounding fails, or you round in the wrong direction, right? And you don't want this. So schemes where you can perform a limited amount of such computations, they are called simply homomorphic encryption schemes. Okay, but we are still lacking the fully homomorphic, right? Fully means that you can do an indefinite amount of such operations, homomorphic. And the way you want to do it is by reducing the error, right? You take a ciphertext where the underlying plain text is an integer with pretty huge error, and you then want to create a new ciphertext which still encrypts the same integer, but now with a smaller error again. Right, because once you have a smaller error again, you can continue to do computations with the resulting ciphertext. And this is all done via bootstrapping. Okay, so what is bootstrapping? I think the idea behind it is very, very fascinating. And to be honest, it took me a while for me to really understand what is going on. So it was invented by Craig Gentry in 2009, and he had the idea of bootstrapping while reading, I think he was currently reading the book Gödel, Escher, Bach from Douglas Hofstadter. So it's really a book trying, and correct me if I'm wrong, but trying to answer the question, what is consciousness and when is a being able to talk about itself, right? Like it's trying to talk about this referencing to yourself, right? We can talk about ourselves, but so we are in a sense a system being able to self-reference. So Craig Gentry was making the connection between these homomorphic encryption schemes and self-referencing. Because in a way, once you have a homomorphic encryption scheme where you can apply any algorithm onto it, well, then also what you can do is you can apply the decryption algorithm onto your ciphertext, but homomorphically. So again, completely in ciphertext space, right? And remember, if you decrypt and your error is sufficiently small, you're able to get back the integer that you're interested in, right? So you do the decryption and then you round and then you get back the integer, right? And if you then go ahead and apply this decryption algorithm, but homomorphically, you're able to get back a ciphertext encrypting the same integer that you're interested in, but with a smaller error, right? Because decrypting removes the error, but since we are doing it homomorphically, there is still always going to be a small error left. So really, homomorphic encryption schemes are, in a sense, able to also talk about themselves, right? Because you're able to apply the decryption while completely staying in this ciphertext space. Anyway, so he had this very impressive insight, and with it, he was able to then transform homomorphic encryption schemes into fully homomorphic encryption schemes. So, yeah, in a nutshell, this is how it works.
Okay, I will probably have to rewind a few times to understand it all. It sounds very cool. And probably this is now a stupid question, but is it that also in this particular case, you're using the same key to encrypt and decrypt, or a different one? Is it symmetrical then in this case or not?
Okay, I see. So in this case, you typically use a public key to encrypt, okay? Mm-hmm. So which is openly accessible to everyone, right? And then a secret key to
so there are two different ones.
Yes, and yes. Maybe I should add, because if you want to apply your decryption circuit, your decryption algorithm homomorphically, you cannot provide your secret key, which is necessary for decryption. You cannot provide it openly, right? But you still want everyone to be able to perform bootstrapping, right? So what do? Well, you do not provide the secret key openly, but you provide an encryption of your secret key, right? And this encryption can still be used to then perform the decryption circuit homomorphically.
It's this moment of the day when I need probably a cup of coffee. So it's not your fault. It's just, there's a lot of analysis. As long as the specialists are doing the right thing, I'm happy, But of course, it's also very, very important that we think about it. And I guess some people don't even realize how much of basically most of the data we're sending is encrypted, hopefully. And all these methods will be used in the future and will be safer, hopefully.
As I said, it also took me in the beginning a very, very long time to really understand what is going on. And to be honest, I only fully understood it once I have just implemented it myself on my computer. Because before that, I wasn't even trusting the entire thing to work. Like the first step is to understand, and then the second step is to really convince yourself that it really also works in practice.
Sounds a little bit like quantum physics, I think. It's a lot of convincing because you can't see it, right? So yes, but anyway, sorry for this irrelevant comment a little bit with two mathematicians, but just you brought me somewhere there. But we have to go back on Earth because we have to solve the pub quiz question. So Jennifer, can you remind our listeners what the question was about and then give us the answer?
Right. So the question was, Mersenne prime is a prime of the form 2 to the p minus 1. P also is a prime number. And the question is, how many Mersenne primes are known? And the answer is that 52 Mersenne primes are known as of 2025.
That's not a lot, is it?
No, it's not a lot. It takes a lot of work to find them.
And you're not onto that particular thing?
Well, I think all of us could be. So there's something called the Great Internet Mersenne Prime Search, where they have software that you can download and use some spare cycles on your computer and maybe find the next one.
Okay, so there are still actually projects where you're using your own computers to research some things. Isn't it all, supercomputers that kind of calculation is done at?
Well, I think, people certainly use supercomputers. People use GPUs. People use various cloud services. I personally run things on my laptop in my office. There are different types of experiments and different types of computations. But the Great Internet Mersenne Prime Search is one of these wonderful showcases of all of us as a community kind of working together to try to uncover new things.
Exactly. Great. And, normally when we talk about citizen science projects, it's, for plants, right? You can take pictures, or there are certain things, SETI and all the astronomical things, but I never heard about the mathematical example. So there you go. We will share the link in the show notes as well if you got interested and you want to do that.
I think there's also something nice about just being able to state that you're part of the team who was able to find the next known biggest prime.
Yeah, of course.
Even if the contribution you had is just a tiny little fraction of the entire computation, but still, you're part of the team.
Yeah, definitely. I agree as well. Why not? So as I said, we will share the link in the show notes and also with all the other things we discussed today. And what reminds us to thank you very much for today. Thank you, Jennifer. Thank you, Tim.
Thank you.
And this is it for today. Don't forget to subscribe, to follow us. We are present on almost all social media, talking about science all the time. Of course, don't forget to suggest guests. And if you want to support us, we are also on Patreon. This was Silex, and my name is Hanna Siemaszko.